Hi there, I got my hands on this multimeter, a Martindale MM68. It's discontinued by Martindale, but you can still find it on the used market. Martindale Electric specializes on electrical testing and safety, so let's have a look if the MM68 is a good choice if you want a safe multimeter instead of the latest Far East toys. Feature-wise, the MM68 sits right in the middle of a family of 3 related multimeters. Apart from temperature, peak measurement and a low-pass filter, it already has all the stuff of the flagship MM94, which is what you would expect in a modern multimeter. I think the only additional function missing is the NCV, but to be honest, I rather use specialized detector sticks with pinpoint accuracy for that anyway. It is interesting that there are 3 off positions. Probably these are places where the flagship had additional functions. The grey holster is slightly rubbery and cannot be removed. It gives the meter a good grip in the hand and on surfaces. There is a very sturdy tilting bail, and it sits very securely on it, no problems. I got it without leads, these are just no-name generic ones. There is no facility to store leads in the holster. There is a green backlight, not very bright in daylight, but okay when you need it, and best of all, it runs for 4.5 minutes according to the spec before turning off automatically. And speaking of that, the meter has auto power off after 30 minutes, but you can disable that if you hold the range button while turning on. Diode mode works pretty much as expected. There is no beep, just a display of the forward voltage or OL in reverse or for open connection. 2 silicon diode in sequence is no problem. A red LED lights up and the forward voltage is displayed. 2 red LEDs light up very dimly but no forward voltage. A yellow LED lights and the forward voltage is shown. A white LED lights but no forward voltage. Resistance now. Auto ranging works very fast, but the display at 1 ohm is way off. This is probably because the probes have not been zeroed out. Let's do that now. Much better. 10 ohm, 100 ohm, 1K, just OL as expected because first I have to get out of rel and back to auto range again. 1K works just fine. 10K, 100K, 1 meg, 10 meg takes a bit to stabilize. 100 meg, no problem. The maximum the M68 can read is 220 meg, which is pretty good. A quick go at continuity. Even with the generic probes, no problem. Capacitance now. The meter shows 64 picofarad, so let's rel that out. 1 nanofarad, nothing, maybe too small. 10 nanofarad, still nothing. Hang on, something is wrong here. The MM68 measures capacitance using the milliamp socket. Very unusual. Just about every other meter I have uses the volts ohm socket for that, so let's try again. Now it works. 1 nanofarad, good. 500 picofarad, spot on. Same for 200 picofarad, very good. I skip testing of other capacitance here. I show the results later and all were okay. Let's just see how long it takes to measure 960 microfarad, my standard test. 4 seconds for the first reading, 6 seconds for stable reading, which is quite fast. Interestingly, the bar graph shows the measuring cycles. I have not seen that in other meters. To test the MaxMin function, I feed the meter with a triangular wave from my function generator. Turning MaxMin on and the readout soon captures the peak positive voltage of about 1.6 volts. Pressing MaxMin again and the display now shows the captured peak negative voltage. Another press of MaxMin and the display shows the current voltage. With 3 updates per second, the readout struggles to follow the triangular wave, but the bar graph with 20 updates per second has no issues. MaxMin is still active in the background and I can display the latest max or min value easily. A long press on MaxMin turns the function off. The MM68 has its own version of input alert. If you leave a lead in a socket for current and turn a voltage range on, it beeps until you fix the problem. It also detects the leads is in a 10 amp socket and you selected microamp or milliamp. And of course the reverse, having the lead in the microamp milliamp socket and selecting 10 amps. Very nice and super useful, but an additional message on the display would help beginners understanding why it beeps, in particular because this feature is completely missing in the manual. Let's have a look inside. First, the battery compartment, which lives behind 2 self-tappers holding the tilting bale. It contains a standard 9-volt battery, also known as PP3. To go further, 3 more self-tappers have to be removed. Then the battery clip has to be pushed inside through an opening of the battery compartment before the bottom shell can be lifted off. There is some shielding foil in the bottom part. I took the complete PCB out to examine it more closely. The black round thing is the beeper, which is much larger than those you normally find in multimeters. It is obvious that protection was big on the agenda when the MM68 was developed. There are 4 gray thermistors and each have been put in the piece of heat shrink for protection. Then we have 4 yellow morphs for transient protection, all clustered around the volts input jack. That's pretty impressive. The 2 red sockets for the currents are using split terminals, and there are these 1 meg resistors sensing if a lead is plugged in and shortening the split. This is how the meter does the input alert I showed earlier. In some meters, the contacts are buried deep in the sockets and a buildup of dust and grime over the years can then lead to false alerts. But in this meter, the split socket contacts are very easy to keep clean. On the left is the fuse holder for the 10 amp 500 volt high rupture current fuse and the 10 amp current shunt in form of the usual wire bridge to the COM input jack. The other end of the 10 amp fuse is going to the 10 amp input jack using a very wide trace that is not only tinned but also stitched with lots of wires to a similar trace on the other side, all to make sure that the trace can handle the current during an overload until the fuse blows. The rupture capacity of the 10 amp fuse is a bit less than Bryman or Fluke, but then these are meters for 1000 volt Cat 4 work, while this one only goes to 1000 volt Cat 2 or 600 volts Cat 3. Given the protection measures in the MM68, these are real Cat ratings and certainly good enough for working for anything in normal house installations. The brain of the meter is a TheHWcave ESS 1921, a 22,000 count multimeter chip which has everything integrated including the LCD driver. It does not include true RMS, but it's designed to work together with another TheHWcave true RMS converter, the ESS636, and this is the solution used in the MM68. The ESS636 is right here. The chipset also supports the additional features of the higher end model like temperature measurement and low pass filtering and even sends data via RS-232, but the wiring for all these are not in the MM68. Interestingly, the monitoring of the split current sockets for the input alert is not part of the features of the TheHWcave chip. This is apparently done with discrete circuitry on the PCB, and that explains why there is only a beep and no message on the LCD when leaving the leads in the wrong socket. By the way, this here is a spring that connects to the shielding foil in the upper part of the housing. Calibration is not done digitally as is often the case now, but using good old trim pots, of which there are 8 in the MM68. Sadly, the PCB does not label what they are for, but with the datasheets of the two chips and the sample application circuit diagrams, it should be possible to figure out what each does. The underside of the PCB does not hold any components except the LCD. Note the wire stitching for the high current path. For a used meter, the traces of the rotary switch still look to be in fairly good condition. Lastly, have a look at how the two housing parts come together. This large overlap is another safety feature. It slides neatly into the bottom part, tightly sealing the gap between the two halves. Anything seriously bad happening inside, like fire, arcing, or fragments of exploding fuses, PTCs, or MOFs, would have to squeeze between the enclosure and the overlapping wall for its whole width before reaching the other side, and possibly hurting a user holding the meter. A quick tour of the performance of the MM68 starting with DC volts. The meter meets its specification. The fact that the error seems to increase on the left is a problem of limited resolution at very small values. At these small values, a single-digit error causes a massive increase in error percentage. Of note, the meter has an increased input impedance on the millivolt range, which is excellent for using it in sensitive electronics. The story on AC volts is very similar to DC volts. The MM68 meets its specs comfortably. Overall, the AC volts are a bit less accurate than the DC volts because of the additional true RMS conversion. I covered DC and AC, but what about AC plus DC, something many multimeters are struggling with? In the MM68, AC volts are coupled over a capacitor, meaning AC with a DC offset such as here is not a problem. But the MM68 struggles a bit with measuring DC with a large AC part. It works, mostly, but the bar graph shows that this is not plain DC. It struggles more if the DC part is very small compared to the AC. Unfortunately, there is not much you can do. This is simply something the MM68 can't measure, but at least it tells you about it through its bar graph. To finish AC volts off, a quick look at the bandwidth. The spec of the MM68 only goes to 2 kHz, but in my test I had no problem far exceeding this. In fact, the -3 dB point was a little over 10 kHz. This was measured at 1 volt RMS, so the results may be different for other ranges. For DC current is pretty much the same as for DC volts. The apparent error increase below 10 microamps is for the same reasons it increases for millivolts. There are just not many digits left at these low ranges. AC amps are generally less accurate than DC amps because of the need for the true RMS conversion, but the MM68 is certainly better than its specs. A quick look at the burden resistance in the current modes. You can actually measure this simply with another multimeter in ohms mode, but especially for the 10 amp range, should null the lead resistance first. With that done, the burden resistance in the 10 amp range is 0.03 ohms, but I bet a large part of this is actually the resistance of the fuse, not the shunt resistor, but for calculating burden voltage, the fuse resistance should be included. Measuring the milliamp and the resistance is 10.84 ohms. Again, including the fuse, 10 amp is quite a high value, better would be 1 or 2 ohms. 1K for microamps is disappointingly high. My venerable Bryman 235 has just 100 ohms in the microamp range. Continuing with resistance, but now as a measurement function, and the MM68 is actually quite good in doing that. The bounciness on the left is again for the same reason as in the other graphs. Of note is that the MM68 can measure up to 220 megohm, which makes it pretty unique in my collection of meters. Other meters have to switch to measure nanosiemens instead of megohms if they cover such high resistances at all. Lastly, capacitance. The MM68 is actually reasonably good at measuring capacitance. The variations are getting larger above 10 microfarad, which is because from then onwards these are all electrolytic caps, and in general measuring those with a proper LCR meter for reference using a sine wave usually gives a slightly different result than the charge-discharge method used by multimeters. And to wrap this up, let's look at battery consumption. For this test, the MM68 is powered from a bench power supply. The voltage is shown by the meter on the right, a WaveTech 25XT, which I will feature in an upcoming video. The current is shown by the Bryman 869S on the left. It turns out that the MM68 consumes between 3 and 4.2 milliamps across all functions. In many modern multimeters, the beeper takes an enormous amount of current. To see if that's the case, I leave it in the continuity mode and then bridge the COM and volts-ohm terminal. About 7.2 milliamps, doubling the normal consumption. That is actually very reasonable compared to other meters. How about the backlight then? A tad about 27 milliamps, so yes, it's expensive in terms of battery consumption as you would expect. Excluding the frequent use of backlight, a 9-volt battery should last the quoted 150 hours stated in the spec for carbon zinc batteries. How low can the battery voltage drop before the battery low warning is displayed? To find out, I lower the voltage from the bench power supply. It's about at the 7 volts mark. That is relatively high because if you use rechargeable batteries, the nominal value may be just 7.2 volts. It should still work as rechargeable batteries keep their voltage relatively constant and only drop steeply when nearly empty. What if you ignore the warning? Does the meter start to produce false reading? The answer is yes, but only after the voltage drops below 5.5 volts. The value shown on the meter should not change, but it keeps going up as the battery voltage drops. It would be better if the meter would shut down at this point instead of showing wrong data. To test the sleep current after the meter goes into APO, I left the meter connected to my power supply but back at 9 volts and recorded the current using my Keithley 195 multimeter, which is pretty good at measuring low currents. The meter beeps just before the APO period expires and then shuts down. The current bounced a bit and then settled to just below 40 microamps. That would be about 1/100th of the operating current. I would still recommend not to leave it in APO sleep routinely and instead turn it off properly, but that's more because of the trickle discharge during sleep may make the battery more likely to leak. While I was waiting for the sleep current to settle, I suddenly noticed that it started increasing again. I turned the camera back on as quickly as I could, about 200 microamp maximum before it starts winding down again. The meter was not touched and appeared to be sleeping unchanged. I analyzed the recording and the top graph covers the whole recording period. The meter is running for 1800 seconds, in other words 30 minutes, at about 4.2 milliamps. Then we see some peaks and a steep drop when the meter shuts down. This is followed by some bumps and then sometime later by another peak. On the lower left, I zoomed into the last 40 seconds when the APO is triggered. There are 3 peaks, which corresponds to the warning beeps telling you that the shutdown is imminent. On the lower right is a zoomed view of the time after the shutdown. There's an initial event with 3 peaks and then about 200 seconds later a much bigger second event where the sleeping MM68 is doing something other than sleeping. I repeated this test a few times and it's fully reproducible. It also left the recording running for quite some time after the second spike and did not see another event. Even during such an event, the current remains rather low, so there is no need for concern, but I would like to know what's causing these peaks during the sleep. Is the MM68 dreaming? Let me know what you think. Since I had the MM68 connected to the Keithley 195, I ran a test where I turned the backlight on and let it time out. It's interesting that the timeout period is clearly 180 seconds or 3 minutes, not the 4.5 minutes promised in the manual. 3 minutes is still okay and much better than the 30 seconds or less that you get from other multimeters. Overall, I think the MM68 is not a bad meter and safety-wise is definitely miles ahead of most Chinese meters. The only real shortcoming I found was measuring small DC voltages hiding under a large AC voltage. Often meters targeting work on electrical installations are not really suitable for electronics, lacking functions or not having millivolts or microamp ranges. The MM68 is a meter that is comfortably at home in both camps, fully featured for electronics and safe to use in electrical installations. If you find it in good condition, it's definitely worth considering. If you like my videos, don't forget to like and subscribe and help growing this channel, and consider becoming a Patreon. The link's in the description. Thanks for watching.